Thank you very much for the introduction and the opportunity. So I think if you got to Venice yesterday, you have a bit of an idea why extreme heat is a problem sometimes, even rain today. But before, so if you actually suffer heat, you can skip half of my presentation. But otherwise, I will provide you now the evidence of why it's quite urgent. But first of all, I would like to introduce the people I'm working with, which are also behind the work I'm going to show today. I'm part of the Architectural Facades and Products Research Group. We are a collective of experts in different aspects of facades, where I work specifically on human facade interaction, and which also translates in different aspects of human facades. And I work very strictly with a group of amazing PhD students. And today I'm showing in particular the work I'm working with QGIN, which is dedicated on resilience to extreme heat. So now, evidence of why it's important. First reason why extreme heat events are worrying us is mortality, death. This is a recent graph from Garcia Leon that provided new statistics on what are the expected number of deaths in 2100 if we keep we are able to meet the current policy recommendation and we keep temperature raise to 3 degrees. So this will mean that anyway, even if we maintain 3 degrees, according to the current policies, there are going to be 60,000 more deaths because of heat. And this death, of course, depends on your personal characteristics. And this is very interesting. Other map shows you how these deaths are distributed in Europe if we also cross-relate with the personal characteristic of the population. So first reason, heat wave have a very strong impact on mortality and death. But heat, extreme heat, has also very important impact on our health and well-being, even if we manage not to die. And interestingly, usually extreme heat is something that has been studied from a physiology perspective a lot. We know very well how to measure and evaluate human resilience on an extreme heat environment in terms of physiological response, which is the first important part, since this affects very much our health. But there is, of course, a very strong impact also on our psychological well-being, our behavioral response. And it's interestingly, we're doing a review to see how people are approaching this problem of how people respond in buildings to extreme heat. And you can see already that physiology is a very high number of papers, but when you start to see two other impacts, it's a bit of a more uncharted water situation where we are still understanding how we can assess human response during extreme heat from a multi-domain perspective. So for many of you that are used to working in seismic engineering or with other type of extreme events, resilience is not a new concept. When we approach a problem from a resilience perspective, what we are looking at, and apologize, this reference is wrong, but we provide a new one, so it's not my graph. So when we're looking at resilience, what we are looking at is we consider a performance, and there is an extreme event, there is a loss in performance, and then a recovery phase, we will probably recover some of this performance. This loss in performance and the time I need to recover my performance are very important when we assess the problem from a resilience perspective. And this creates a very big difference between approaching the problem of extreme heat from a comfort perspective towards an extreme event or resilience perspective. Because in comfort, what we try to do always is to maximize satisfaction. While here, we are not trying to maximize satisfaction, we are trying to resist, recover, and minimize the losses. So also the thresholds of tolerance become higher. If we translate this in a curve of people response, it means that the extreme heat event is coming, temperatures are rising, so our thermal discomfort, physiological response, psychological distress increases. There is a time we are in the middle of the heat wave, the temperature is high, gets steady, and then gets down, and we recover. And so we could apply this to people. And then you already see how important it is to have a temporal understanding of this phenomena, because then we want to look at how much time it takes me to get to the maximum level of distress, how long I can stay in that distress, what are the consequences of staying in the distress, and how long it takes me to recover. So all the aspects of the curve become to be important. Interestingly, it's not a matter of avoiding exposure to heat, because this curve in people can adapt, in the sense that the more we expose people to heat, the more our capacity for adaptation increases, and our flexibility and resistance to the extreme heat improves. This is very similar to what happens in fitness. For the whom you are sporty, you know that when you start to run or start to do your sport, you increase your fitness. Then, of course, if you stop to do sport and exercise, your level of fitness decreases. But then, if you start to exercise again, your body remembers that it has been exercising. And for heat, it's very similar. But of course, we need to know what is the maximum safe temperature we can expose people, and also to help their adaptation. So up to now, we have been looking at the people perspective. Usually in our assessment, we actually look at the building perspective. So we look at how high is going to be the temperature indoors. What we will try to see in this presentation is what it takes to have a human building perspective, where we want to combine both the personal response to an extreme heat event and the building characteristics, because as you know, they influence each other. The actual people you have in the building set your maximum safe temperature, but also their behavior impacts the performance of a building. So it's important we take both together. So this means that we can think on the people as the sensitivity aspect that marks the threshold we can use to resist, buildings as the exposure, so the filter between outdoors and indoors, so how much I'm going to expose to people, to what condition, but how sensitive are the people to that condition will depend on individual characteristics. And then I can put in place, as a building engineer, different technologies to adapt and change the facade, which is our passion here, or the cooling system, or the combination of the two. So I would like now to briefly show you some preliminary evidence on why the type of weather file we're using makes a difference, the type of metric that we use also plays a big role, and why we need to shift from deterministic to probabilistic approaches when we assess the resilience of facades and people to extreme heat. So we did a case study. We compare, for instance, Italy, Naples, to the Netherlands, where I'm based now. Let's look at this part of the graph, for instance. This shows you what happens if we consider the typical meteorological year, which is the typical weather file we're using in our design, which is the result of a statistical process where we are taking the typical map for a span of years, and we want to have a statistical good representation of a typical weather. You can already see that even if we take that file and we morph it to consider the projection on 2080, that projection is already outdated if we compare it to a historic heat wave that happens now. So it means that even if we start from the design inputs of the weather files we can use nowadays in the design process, and we morph them to follow the climatic projection of the IPCC, even then we have outdated data. But of course, the question that we have in general is, what do we use for designing? Should we design then with extreme data peaks, or we still want some statistical representation of what is future a good consideration? And this is very important, because if we only consider extreme peaks, we're going to oversize our system. And because, as Ulrike explained very well, we are in a situation where resources are limited, we need to strike a balance between meeting an extreme event, but not oversizing extremely. And this, of course, it's a trend that is much more visible in Mediterranean countries, where the extreme heat events are worse, but also in the Netherlands. Metrics. How do we measure then resilience? It's a matter of seeing the temporal evolution of earth temperature. It's a matter of measuring heart rate on people. What do we take as an indicator? And how this affects your design in the facade. So we did a sensitivity analysis where we considered a facade, and we tried to see 500 variations in properties from heat, density of the layers, thermal conductivity, window-to-wall ratio, characteristics of the glazing, to look at two things. If changing the metric changes the final facade design, but also how important is the facade in responding to the extreme event. So I go back to the first graph I showed you, where you see the temporal evolution during an extreme heat event, where we have a robustness period where the extreme heat event is picking up and you want to resist. Then the middle of the heat wave event where you want to resist, and the recovery phase. I won't go into the detail, but what I want to show with this matrix is that it's showing the correlation between the different type of metrics, and the one that we can use to measure recovery, robustness, and resistance. And you can see that where recovery and resistance are quite correlated, robustness is inversely correlated, but more importantly, there is very low correlation between robustness metrics and recovery, which means that if we design a facade only considering one of these phases, we might end with different type of facade than if we consider another type of the phase of the extreme event. So we need to consider all the different type of part of the event, and then optimize toward an optimal solution, because these criteria may have competing requirements in terms of facade performance. If we put weather and metrics together, this shows you, for instance, for a case in Naples, if we want to design a new facade for this building, you can see for each different metric how important is the facade, because it's basically defining the width of this box plot. So the higher the box plot, the higher is the impact of facade variation on the metric. And you see two tendencies that are interesting. One is that regardless of the metric, the more extreme is the event, the lower becomes the variance, meaning that, of course, facades still play a role, but extreme events narrow down the impact of the variations. So still it's important to be in your optimal area. And also shows you the difference between using design files, depending on the metric, and then extreme weather events. Now, the question, what is the most important parameter in a facade in an extreme heat event? So the sensitivity analysis we did, I don't want to go into detail, but I would be happy to explain later in coffee break. If we consider a facade that has always a level of insulation of at least 5 centimeters, you start to see that the parameters that play a very important role are G value, the glazing U value, the window-to-wall ratio, the ventilation area. I think this we might have guessed without the sensitivity analysis. What I think is interesting is that if we consider the typical meteorological year, so the current input we're using for design, so the weather files we are all currently using in our design, we consider an extreme event, a weather file built upon an extreme event on a projection of later on, you see that even if some of the tendency exacerbates, the trends are similar. So the parameters that impact the thermal performance of a facade are still the same. So this good news, means that we are not starting from zero. Finally, last thing I would like to show, why it's important to move from a deterministic approach to a probabilistic one. So there are uncertainties, as you know very well. The uncertainties are related to material properties, behavior of people, but also, as we saw before with the weathers, on actually the prediction of what is going to be the hazard, the event that we are designing for. This means that considering one weather scenario, two weather scenarios, may be leading us towards a wrong design. If we have a probabilistic approach, we can instead build a probability of response in our building, considering the probability of an event. So this means that I can consider different, for instance, heat waves with different probability that will affect the building with a different probability. So have a different probability of reaching my limit state, and I can build a fragility curve. This doesn't sound new at all for the whom you are working on structural engineering, but it was never been applied in comfort, or very, very rarely applied to comfort. What we're trying to do here is to apply the concept of fragility curve to the assessment of the performance of a facade and a building in extreme heat. And therefore, the question is, can I build a fragility curve that can describe the response of my building, and even better, the people in the building and that building to an extreme heat event, by setting, for instance, as a limit state, a level of standard effective temperature that the society decides to be the benchmark of a safe temperature. The first step is, of course, to gather the data, first of all, on the hazard, and then on the probability of response of the building. So it means that differently than the first work I was showing, I cannot take one weather file, one heat wave. I need to consider several heat waves and how these heat waves can happen, the probability of this heat wave to happen in our country. Then I can build a probability of an hazard to happen. I can have then a fragility curve that describes the response with the building to the probability of the hazard, and then calculate the losses. So, for instance, if we do this for different facades, then we can compare them in terms of the probability of exceeding our limit state. And it may happen, like in this assessment we did, the different facades may be ideal for some hazard intensity, but not for others. And this, I'm sure, sounds very familiar for people in seismic. And even more interestingly, if we're designing for multiple hazards, seismic and heat and floods, we can then use both fragility curves to find our optimal solution and give resilience scores to our facade in each of the hazards. This is still work in progress, of course. But to conclude, main take-home message. So facade resilience to extreme heat requires a different approach than designing for thermal comfort. And type of metric, the weather inputs I use for my design have a major role in assessing the fragility, the vulnerability of your building. The same facade properties that we always use to be designing with play a key role. So this is not new for us, but because very important to consider the temporal evolution during an extreme heat event. What is missing? A lot. The main problem we have is that we don't know what is the maximum safe temperature and what are the limits of resilience of each of us, because we are so different within each other. And designing for one standard person doesn't work anymore, because this then, as you have seen from the first graph, mortality is really individual characteristic dependent. Today I show mainly simulation work we've done with my research collaborators, but actually we are working very hard in experimenting, gathering experimental data on people response, either, for instance, like here, to different facade properties under extreme heat, or to different combination in real buildings. But this is an area where all our effort is required, because we need data also to build the fragility curve, and the data is not there. So altogether we need to collect evidence of what is happening nowadays in the heat waves in our buildings. To conclude, Auliki was saying who is studying, few people. So that's why, together with my colleagues and friends from EURAC that are here in Darmstadt, we have a new project, which is an Erasmus Plus project, where we are creating 6 completely free open education programs online that investigates and focus on several aspects of new performance aspect of facades, starting from theory and technology, out to detail, which is something that often when you are starting in facade design engineering, you are lacking experience with, up to performance-based design, circularity, and innovation. So follow us. We are launching slowly the content. The first MOOC is coming in 1 month. Thank you very much.